I-beam. Thumb upright equals 1.20. This I-beam is used to support the first floor of a house. An I-beam, also known as H-beam for universal column, UC, W-beam for wide flange, universal beam UBE, rolled steel joist RSJ, or double T especially in Polish, Bulgarian, Spanish, Italian, and German, is a beam with an O-shaped cross-section. The horizontal elements of the are flanges, and the vertical element is the web. I-beams are usually made of structural steel and are used in construction and civil engineering. The web resists shear forces, while the flanges resist most of the bending moment experienced by the beam. The Euler-Bernoulli beam equation shows that the I-shaped section is a very efficient form for carrying both bending and shear loads in the plane of the web. On the other hand, the cross-section has a reduced capacity in the transverse direction, and is also inefficient in carrying torsion, for which hollow structural sections are often preferred. History. The method of producing an I-beam, as rolled from a single piece of wrought iron, was patented by Alphonse Halbu of the company Forges de la Providence in 1849. Bethlehem Steel was a leading supplier of rolled structural steel of various cross-sections in American, British, and skyscraper work of the mid-20th century. Today, rolled cross-sections have been partially displaced in such work by fabricated cross-sections. Overview. Thumb upright equals 1.20 typical cross-section of I-beams. There are two standard I-beam forms: rolled I-beam, formed by hot rolling, cold rolling, or extrusion depending on material. The girder, formed by welding, or occasionally bolting or riveting plates. I-beams are commonly made of structural steel but may also be formed from aluminium or other materials. A common type of I-beam is the rolled steel joist RSJ, sometimes incorrectly rendered as reinforced steel joist. British and European standards also specify universal beams UB and universal columns UX. These sections have parallel flanges, as opposed to the varying thickness of RSJ flanges which are seldom now rolled in the UK. Parallel flanges are easier to connect to and do away with the need for tapering washers. UC of equal or near equal width and depth and are more suited to being oriented vertically to carry axle loads such as columns in multi-story construction, while UB are significantly deeper than they are wide are more suited to carrying bending loads such as beam elements in floors. I-joist I-beams engineered from wood with fiberboard and slash or laminated veneer lumber are also becoming increasingly popular in construction, especially residential, as they are both lighter and less prone to warping than solid wooden joists. However, there has been some concern as to their rapid loss of strength in a fire if unprotected. Design. Thumb upright equals 1.20 illustration of an I-beam vibrating in torsion mode. I-beams are widely used in the construction industry and are available in a variety of standard sizes. Tables are available to allow easy selection of a suitable steel I-beam size for a given applied load. I-beams may be used both as beams and as columns. I-beams may be used both on their own or acting compositely with another material, typically concrete. Design may be governed by any of the following criteria. Deflection. The stiffness of the I-beam will be chosen to minimize deformation. Vibration. The stiffness and mass are chosen to prevent unacceptable vibrations, particularly in settings sensitive to vibrations, such as offices and libraries. Bending failure by yielding, where the stress in the cross-section exceeds the yield stress. Bending failure by lateral torsional buckling, where a flange in compression tends to buckle sideways or the entire cross-section buckles torsionally. Bending failure by local buckling, where the flange or web is so slender as to buckle locally. Local yield, caused by concentrated loads, such as at the beam's point of support. Shear failure, where the web fails. Slender webs will fail by buckling, rippling in a phenomenon termed tension field action, but shear failure is also resisted by the stiffness of the flanges, buckling or yielding of components, for example, or stiffeners used to provide stability to the I-beam's web. Design for bending. Thumb upright equals 1.80. The largest stresses, sigma Roman 20, in a beam under bending are in the location farthest from the neutral axis. A beam under bending sees high stresses along the axial fibers that are farthest from the neutral axis. To prevent failure, most of the material in the beam must be located in these regions. Comparatively little material is needed in the area close to the neutral axis. This observation is the basis of the I-beam cross-section. The neutral axis runs along the center of the web, which can be relatively thin, and most of the material can be concentrated in the flanges. The ideal beam is the one with the least cross-sectional area and hence requiring the least material needed to achieve a given section modulus. Since the section modulus depends on the value of the moment of inertia, an efficient beam must have most of its material located as far from the neutral axis as possible. The farther a given amount of material is from the neutral axis, the larger is the section modulus, and hence a larger bending moment can be resisted. When designing a symmetric beam to resist stresses due to bending, the usual starting point is the required section modulus. If the allowable stress is and the maximum expected bending moment is, then the required section modulus is given by $S equals \C frac M \math max sigma math max equals frac I C where is the moment of inertia of the beam cross section and is the distance of the top of the beam from the neutral axis. See beam theory for more details. For a beam of cross-sectional area and height, the ideal cross-section would have half the area at the distance above the cross-section and the other half at a distance below the cross-section. For this cross-section, $I equals \frac R24 quad south equals \frat 12 However, these ideal conditions can never be achieved because material is needed in the web for physical reasons, including to resist buckling. For wide flange beams, the section modulus is approximately 0.350, which is superior to that achieved by rectangular beams and circular beams. Issues. Though I-beams are excellent for unidirectional bending in a plane parallel to the web, they do not perform as well in bidirectional bending. These beams also show little resistance to twisting and undergo sectional warping under torsional loading. For torsion-dominated problems, box beams and other types of stiff sections are used in preference to the I-beam. Shapes and materials U.S. Shapes and materials U.S. Thumb upright equals 1.10 rusty riveted steel I-beam. In the United States, the most commonly mentioned I-beam is the wide flange W shape. These beams have flanges whose inside surfaces are parallel over most of their area. Other I-beams include American Standard designated S shapes, in which inner flange surfaces are not parallel, and H-piles designated HB, which are typically used as pile foundations. Wide flange shapes are available in grade ASTM ANN 192, which has generally replaced the older ASTM grades of 572 and A36. Ranges of yield strength A36 a 572, with the most common a 588, similar to a 572 and 192. Like most steel products, I-beams often contain some recycled content. Standards. The following standards define the shape and tolerances of I-beam steel sections. European standards. EN 10024 hot rolled taper flange I section tolerances on shape and dimensions. EN 10034 structural steel INH sections tolerances on shape and dimensions. EN 10162 cold rolled steel sections technical delivery conditions dimensional and cross sectional tolerances. ACE Manual. The American Institute of Steel Construction ACE publishes the Steel Construction Manual for designing structures of various shapes. It documents the common approaches, allowable strength design ASD and load and resistance factor design LRFD, starting with 13th ed to create such designs. Although DAN 1025-5 ASTM-6 American Standard Beams BS4-1 is 808 dimensions hot rolled steel beam, column, channel, and angle sections Z/NDS 3679.1 Australia and New Zealand Standard. Designation and terminology. In the United States, steel I-beams are commonly specified using the depth and weight of the beam. For example, a W-22 beam is approximately in depth nominal height of the I-beam from the outer face of one flange to the outer face of the other flange and weighs. Wide flange section beams often vary from their nominal depth. In the case of the W14 series, they may be as deep as. In Canada, steel I-beams are now commonly specified using the depth and weight of the beam in metric terms. For example, a W250-33 beam is approximately in depth height of the I-beam from the outer face of one flange to the outer face of the other flange and weighs approximately. I-beams are still available in U.S. sizes from many Canadian manufacturers. In Mexico, steel I-beams are called IR and commonly specified using the depth and weight of the beam in metric terms. For example, I-450-33 beam is approximately in depth height of the I-beam from the outer face of one flange to the outer face of the other flange and weighs approximately. In India, I-beams are designated as ISM, ISB, ISB. ISM, Indian Standard Medium Weight Beam, ISB, Indian Standard Junior Beams, ISB, Indian Standard Lightweight Beams, and ISB, Indian Standard Wide Flange Beams. Beams are designated as per respective abbreviated reference followed by the depth of section, such as for example is 450, where 450 is the depth of section in millimeters mm. The dimensions of these beams are classified as per as 808 as per BIS. In the United Kingdom, these steel sections are commonly specified with a code consisting of the major dimension, usually the depth x, the minor dimension x, the mass per meter, ending with the section type, all measurements being metric. Therefore, at 152 and 152x23 UC would be a column section UC equal universal column of approximately depth 152 mm, width and weighing of length. In Australia, these steel sections are commonly referred to as universal beams UB or columns UC. The designation for each is given as the approximate height of the beam, the type beam or column, and then a unit meter AD/G. A 460 UB 67.1 is an approximately deep universal beam that weighs. Cellular beams. Cellular beams are the modern version of the traditional castellated beam, which results in a beam approximately 40–60% deeper than its parent section. The exact finish depth, cell diameter, and cell spacing are flexible. A cellular beam is up to 1.5 times stronger than its parent section and is therefore utilized to create efficient large-span constructions.